Hello everyone, my name is Mohammad Reza and I'm presenting for 2020 Virtual AIChE Annual Meeting. The topic of my research is machine learning approach to model corrosion rate as a function of time. Ramin Mehrani and Dr. Samit Sharma were also part of this project. The outline is as follows. Introduction, we'll see what's corrosion and how it impacts the pipeline's failure. And then we'll see what's machine learning in a short sentence, and then I'll talk about different learnings. In the method section, I'll talk about the machine learning algorithms that we have used and how we tune them to predict the corrosion rate for us. Then I'll show you the results of the corrosion rates predictions versus time. And finally, I'll have the conclusions followed by the questions. Introduction. Internal and external corrosion in the oil and gas industry is a major concern. And as you see on the figure on the left, 22% of the pipeline's failure is due to the corrosion. And that's a huge amount of money, even more than billions of dollars. A widely used method to lower the internal corrosion of oil pipelines is injecting corrosion inhibitors. And it's important to monitor the corrosion rate as a function of time in the presence and absence of corrosion inhibitors to ensure that the failures are timely detected. That will gives us an estimation to when is the best time to inject a new corrosion inhibitor into the system, and that's what we are looking for in this particular project. So experimentally measurements of corrosion rate as a function of time is expensive and time consuming, and there are two types of experiments: sequential dose and single dose. Sequential dose are something like what we have on the left figure, that we are injecting the inhibitors gradually, and with that we are increasing the corrosion inhibitor concentration, and respectively the corrosion rate decreases gradually. On the other hand, the single dose experiments, the corrosion inhibitor is added all at once at the very beginning of the experiments, like here. After 5 hours, the 100 ppm of the corrosion inhibitors is added to the system, and that's it. We are not adding any more corrosion inhibitor to the system, and we are monitoring the corrosion rate afterwards. So what's the goal of this project? Our goal is to implement a strategy to train a machine learning model that can reproduce the outcome of these experiments. Basically, we are looking for some models that predict corrosion rate as a function of time for us exactly the same as what we see in these figures that yielded experimentally. So very short and simple definition of machine learning is constructing computer programs that learn from experience to perform well on a given task. There are three types of machine learning: supervised, unsupervised, and reinforcement. In the supervised learning, the task is to identify the relationship between inputs and outputs, which are already labeled with humans. An example of this kind of learning is image binary classification of cats versus dogs, for example, or detecting spam emails versus non-spam emails, and also even predicting the weather or forecasting the weather for tomorrow. The unsupervised learning, on the other hand, the task is identify the relationship between inputs and outputs where no human is involved in. And in these kind of learnings, we are looking for the machine needs to discover undetected pattern from the unlabeled samples. An example of this kind of learning is clustering of regions of city into, for example, uptown, downtown, midtown, and residential. And although that there is no exact boundaries between these regions, but the machine with the help of the features like number of commuting, population in the morning and the night, and traffic, we'll understand and will show us and we'll cluster these. We'll make cluster for us based on the features that we are providing to it. And I'm not talking about the reinforcement learning in this project. And our focus of what we have used in this case study is supervised learning. The basic steps involved in developing a supervised machine learning models are as follows. First, we need to prepare the data set. By preparing, I mean all the cleaning and transforming everything. Then we split the data into training and testing. And then we have to compare our models that we already selected them what models we have, but we need to compare them with their best performance, with the best architecture and hyperparameters. Basically, this step is tuning the hyperparameters and comparing the models. Then we will fit the best model that we have found from step 3 with the training data. And then we are validating the model performance by doing cross-validation, etc. And finally, we predict for the unseen data and report the error. And now we are able to predict for the production set, which is completely unseen and is completely new data. Methods section of this project. The dataset that we are given, it has 25 experiments that yielded from 4 different labs. The experiments are repeated many times. By that I mean that in the labs, because they wanted to be sure that the corrosion rate that they are detected versus time is correct, they repeated that experiments many times. So we ended up with many replicas for each experiment. The total number of data points found to be 35,082, and we had 13 features to define each data points, 5 categorical and 8 numericals. The categorical features are shown in gray color in this table, and then the numerical features are colored in orange. And the target variable for us was corrosion rate, number 14 in this table. So I'm just showing you what are the features here. The first feature is corrosion inhibitor concentration in ppm. Then we'll have time in hours. Then CO2 partial pressure in bar, temperature in degree of Celsius. Then we'll have the corrosion inhibitor type. We had 2 types of corrosion inhibitors, which is categorical feature for us here. Then we had the shear stress in Pascal, and then brine ionic strength, brine type, pH. pH was not numerical for us here because experimentally in most of experiments they did not control the pH, so we had control at uncontrolled. And then we had type of experiments, sequential dose and single dose, as I just showed you in the previous slides. And then we had prior corrosion inhibitor concentration, pre-concentration 0, and initial corrosion rate. So I should say that the first 10 features here are experimentally given. However, we added those 3 at the very end to help us to capture the effect of injecting inhibitors into the system. So we chose them ourselves, and as I said, the target variable for us here was corrosion rate in millimeter per year. So to facilitate and enhance the learning process, we had to do some pre-processing. The first step was data cleaning, and we had to do that to ensure that the given data from different labs are consistent in terms of labels, units, and positions, etc. And the second was data transformation. As I said, we had 5 category of features that they had to be translated into dummy features first. Then we also transform all numerical features. We scaled them or normalized them somehow that we ended up with a mean of 0 and a standard deviation of 1 for each feature. And I should say that the time, which was a numerical feature, but we did not scale that, but instead we set it to be 0 at each injection time to successfully help us to capture the effects of the increasing corrosion inhibitor concentration on the corrosion rate. Here I'm showing you the machine learning algorithms that we have used in this project. The first one is artificial neural network, which is also known as multi-layer perceptron or MLP. Then we have support vector machines, random forest, and k nearest neighbors. And for all these, we had to come up with some tuning hyperparameters methods first. So for that, we divided the data into 75% training and 25% testing. And then we did fivefold cross-validation with the exhaustive grid search algorithm. And we make sure that we did that 20 times to ensure that at the end, when we are taking the average, always, I'm sorry, always we get the same results. So here I'm showing you the tuned hyperparameters value for each model. For MLP, we chosen two hyperparameters, number of hidden layers and number of neurons per hidden layer. And on this figure, in the blue, we can see that we found out that the number of hidden layers of 5 with the neurons per hidden layer of 10 gives us the smallest values of the mean square error. For SVM, we found that the cost of thousands and the gamma 0.01 is the best model that we can have for SVM. For the random forest, we found that the number of estimators or trees of 500 and max fraction of features of 0.6 gives us the random forest performance model. And then for KNN, we found that the number of neighbors of 3 with the weighting algorithm of distance, not uniform, is the best. So then we compared these best models of each algorithm together here in this figure I'm showing you, and we saw that the random forest with the number of trees of 500 and max fraction of features of 0.6 has the best performance for us with the MSE of 0.002. And hereafter we use this model to predict further predictions for us. And as you see here, the random forest performance in the parity with the parity plot, the MSEN mean absolute error, everything is real small, which is good. And I should note here that this parity plot is based on 75% 25% splitting data. Results. First, let's see the predictions for sequential dose experiments. Now that we want to see what's the predictions of the corrosion rate versus time, I should say that we did not split the data into 75% training, 25% testing. And instead, we put aside 5 experiments out, and we trained our model with the 20 experiments. So in total, we had 25 experiments. So I removed 5 experiments initially, and we chose those experiments randomly. And we trained the model with 20 experiments, and we found the predictions for those 4 experiments. And this figure on the left, I'm showing you the experiment number 2, and as you see, the testing were experiments 2, 17, 25, 29, and so these 4 experiments were out in the whole process of the training. And as you see, the prediction is close enough to the replica one, or it's close enough to the basically the experimental data. And on the right side, I'm showing you experiment number 4, where experiments number 4, 7, 14, and 24, they were out at the time of training. And the results is close enough, and but there is some discontinuous behavior at the point of injections, which is not realistic, but on the other hand, it shows that our model could get the effect of the injecting the inhibitors in the system, and that's good. And also I should say that the very last the corrosion rate at the equilibrium is close to the experimental, which is good, and that's what we're looking for. Next, I'm showing you the single dose experiments predictions. We did the same steps. We put aside 4 experiments out, or 5 experiments out, and 20 experiments in our training set. And as you see here, experiment number 17, our prediction is very close to the experimental. In experiment number 12, our prediction is in between of the experimental data. In number 14, our prediction is very close to those experimental data that they had the corrosion rates higher. And for experiment number 23 is the same, that our prediction was a little bit overestimated of the experimental data, which is if we look at the y-axis that is in logarithmic scales, it's not that far. So for sure, I mean, to assure that our model is working well, we try to do some production sets as well. So for that, we did the sensitivity analysis by varying the features, values, and see how they affect the corrosion rate versus time plot. For that, for example, we changed the corrosion inhibitor concentration from 10 to 500. And as you see in this figure on the top left, we see that by increasing the corrosion inhibitor, the corrosion rate decreases, and that's what's expected. And also we looked at the CO2 partial pressure effects. We changed the CO2 partial pressure, and we found that they are directly correlated. It is directly correlated with the corrosion rate, and same thing found for the temperature. All these was expected, but these helped us to make sure that our model works great. And I should say again that all these uh, experiments, they were not in our training or testing set. They are all completely new, and now we have some predictions for them, and that's what initially we were looking for. In conclusion, I should say that the machine learning models are quite useful in modeling the performance of corrosion inhibitors, and machine learning models were able to capture important characteristics of the experiments, including the impact of sequential dosage and single dosage amount, time trend of the corrosion rate, and the final corrosion rate as well. And machine learning models can be used to predict outcomes for the conditions that have not been studied experimentally. And that's what we found we saw from sensitivity analysis we did. And an important note that I should add at the end, a word of caution, that a machine learning model only predicts what it learns from the data. And there is no guarantee that the machine learning model prediction is more accurate than the experimental results. And with that, I'd like to thank you all, and I'm ready for any questions that you have. Thanks.